my slides. Now, can you see that? Not yet. I have to. Yes. So.
Yep, we can see it perfect.
You can see that. In fact, here's the title. Can you see the title? Is this full screen? Not yet.
Yeah,
huh?
no, it's not full screen, but we can see.
I try full screen. Oop. Does not really work for some reason. Now.
Oh, yeah, perfect.
Okay. Okay. Yeah, for me, it's good morning, everybody. It's really a pleasure for me to speak in this colloquium in honor of John. We have made so many things together, and for the last 20 years, we were not so much in contact. So it's good to see you again, John. So this is joint work with Rolf Hennecke and Alexander Knapp, former students, now established researchers, one of them also already an emeritus. Well, the young people get older, that's the problem, or that's reality, in fact, not a problem. I will talk today about the topic epistemic ensembles. Well, I'm a newcomer in this epistemic area. We were working on ensembles. This is also collaborating agents in a system from the software engineering point of view in the last couple of years. And I tried to somehow fit some epistemic issues in there. So let me just first come back a little bit. You hinted at that, Guillermo, John and me. This was at an occasion in Munich many years ago in the 90s. We were both younger, but John looks still as, oh, very, very good now, and not so much different. So the first meeting we had in Munich, I was a PhD student of Kurt Schütte, and I think we met in a party at Schütte's home. And then there was the point that I was going to my first conference, the Logic Colloquium in Clermont-Ferrand, in order to talk about first results in my PhD. And I was going there by car. And somehow it turned out that John needed a ride. And so we were traveling together to Clermont-Ferrand, and then also a meeting there, Peter Peppinghaus. And the nice thing is, I think John told it also in his talk formerly, that we were not really, we had really difficulties or not difficulties in communicating, because me at the time didn't speak English at all. John was speaking French and English. I was speaking German and French, and Peter Peppinghaus was speaking German and English. So we had a kind of common ground, but not quite, but we managed, and it was really a very nice event, and we had many beers and wines together, and so it was a nice starting of our friendship. And then later, when I was in Passau, and then later in Munich already, John visited me regularly in Germany. And we started to do some work together. I was very happy about that. I was also in Melbourne. I was very happy about that because John was also doing a co-supervision of my students. They needed logic help quite often. And so the first one where John was really involved was the PhD student Luis Mandel, where I think, John, you are speaking Spanish as well. So Luis is Argentinian, and so they had a very nice relationship. What we did at that time, I come back on the next slide, is the so-called constrained lambda calculus. And after the PhD of Luis, successful PhD of Luis, we had another work together. Guillermo hinted at that, namely working on extracting structured programs from specification proofs. I'm working, well, since the beginning, since the 70s. In fact, I was working in the area of algebraic specification and software engineering, how to construct, to build correct programs from formal specifications, in particular structural algebraic specifications. And here I come back to this also in a minute. And this was joint work with Iman Poinome, very enjoyable. Iman was also several times in Munich, and well, good time. So what will I do today in this talk? I will, well, firstly talk about my work with John, and then trying something out, which what I'm calling epistemic ensembles. We were working in the area of so-called ensembles in software engineering in the last years. And I always try to put logic in there. And so I will present you, I think, a new sequent calculus for dynamic epistemic logic. I'm surprised that this does not exist, but maybe it's a little bit inconvenient. It's a little bit not a normal kind of sequent calculus. I'm looking forward to your reactions, and then very shortly go into the topic of constructing correct realizations from epistemic requirements. So, first order constraint lambda calculus. What was the idea of this work? We heard already today, there was the time of logic programming in the 80s, in the 70s and 80s. And what was interesting in this logic programming is that even if you do kind of normal programs, it's interesting to have constraints where maybe there's incomplete information. And so what we tried in this work is to extend the lambda calculus with so-called first order constraints. A very simple example you see here. If you want to calculate the area of a triangle, then this is too much. Then you can, if you have a right angle triangle, you multiply L1 times L2 at the both lengths, divide by 2. And then what you need to have is just that these lengths are greater than 0 in order to have this. This is very simple constraint. Nobody will think about it. But if you make this a little bit more complicated in order to calculate the area of a triangle where you do not have full information, you only know that, well, the usual inequalities, A here is smaller than B plus C, B is smaller than C plus A, and C is smaller than B plus A. So the triangle inequations, and then you can compute the area of the triangle by just dividing it into two rectangular triangles with a right angle, and then you just calculate the area of this rectangular triangles and this one here with. So here you calculate p squared plus h squared and so on, and here the other side, h must be greater than 0. So this is a constraint, and you put this into the lambda calculus. We also have here first order constraints. We also have here existential quantifiers, because these are auxiliary variables here. So we get a term where we calculate here this the lambda term with the help of a constraint. So this is a nice calculus, but of course Luis had difficulties in putting these things right. with the help of John, he could prove many things. For example, George-Russell properties. And also he is a computer scientist, Louis, so he built a system where you can compute such equations in particular. While the system helped more with linear equations. At that time, the computers were not so strong that we could really do higher order stuff. And so a nice thesis came out of this work. We wrote several, well, 4 joint papers with Louis and John. The second work, which was a bit later, and at the end with Iman Pornomo, was the idea that the Curry-Howard correspondence, of course, could be used, is used in type theories, but also could be used for structured algebraic specifications to get correct programs. Also here we had a series of papers. The first one was with Hannes Peterreins, a student of mine who did logic, and he was working and constructing in his thesis a natural deduction calculus for this structured algebraic specifications, and there was a paper coming out together also with John. In fact, I think we wrote the paper. Hannes was already in industry at that time, but the basis was his work. And then the work with Iman were on extracting the programs from specification proofs, which was extended to parameterized specifications, and then turned out to be a very nice book based on the thesis of Iman, adapting proofs as programs to Curry-Howard protocol. So let me just give you a hint, an idea how this worked at that time, how we did this work. So what are these structured specifications? In fact, these algebraic specifications consist of a signature and a set of axioms. Axioms are typically equation-based in this algebraic surround. And then there are operations on these specifications in order to build structured specification. The simplest one is union, join 2 specifications together. Then you have some kind of translation and renaming, where you can change the names of the signatures in a coordinated way. The simplest examples here from the paper extracting programs from specifications is you have natural numbers. Okay, you see here the signature, sorts and operations and predicate symbols and some axioms. Oops, sorry, this was too fast. And here you have the first very simple structured specification, because you here extend this not zero specification by some other stuff that can be more complicated, here just with a constant. And then the question, how does a Gensen type proof system look like? Here, of course, if you want to construct programs, a constructive Gensen type natural deduction system, what we have, you take the usual system, here the logical rules, introduction for quantification, and you add structural rules for this, structural rules for the specifications. So here, in order to introduce an extent, well, we prove a formula A within a specification. The proof term somehow represents here, well, the proof, and then we embed this proof. Sorry, should have started in the beginning here. What is in the logical rules, what we do in addition is we say in which specification this formula is proved. So, and this can change if the specification is structured, if you take more axioms and so on. So if you have a union and have proved A with the proof term D in the specification SP1, then we can inject that into a more complicated, this is simple, but in a more complicated, larger specification here, and the proof term just reflects the specification operation, and this on the right and left hand side. So what we can prove here is that this is this calculus is sound and complete. Oh, sorry. The main theorem was that the system is sound and complete. And using this, one can extract programs in the usual way. Oops. You can extract programs in the usual way. If I have a specification SP and the proof, constructive proof of a formula, then I can build an executable refinement specification, so refined specification, which is executable. And from the proof term, we extract a structured program. The theorem here is written there. It just says this, how we can construct. Then here is a little example. Sorry, I have a problem with this. Here, excuse me, here. Here is a little example where we want to prove just that there exists a constant, but suppose we have a constructive proof. This is the example we do in the paper, which you can represent in a paper, but we did, of course, more interesting stuff. So then in order to show this, we construct out of the proof for this for this constant. Well, we construct a proof, and in this proof, we see that we get a structured specification which involves three. I'm sorry, I don't know what's going on here. Is my computer again? We have an executable specification which we construct out of this proof. Here you see this structured specification, and the corresponding proof term after extraction program gives the following structured program, namely, which is very similar to that what we have seen here, that you have a structured lambda term, which also involves some hiding operators, which of course one can then later turn into a normal lambda terms. But we get executable specifications and structured programs. So then this was the work we did end of the, well, at the turn of the century. Now I come to some new small results we are trying to, we are just investigating now. A similar idea, we are in a concurrent situation when we have requirement specifications for a system where we want to construct processes which satisfy these requirement specifications. So we develop programs from specifications as we did with John. I will not use Curry-Howard. This seems to be complicated. I tried first starting with this, but we are not yet at that point. Maybe, John, I will need your help for this. So what is the approach? We use kind of standard, what Liz has described, epistemic logic, as shared knowledge for collaboration between agents. I will show you a much simpler example than Liz showed you. Communication between the agents is by knowledge announcements. We describe requirements by dynamic epistemic logic formulas and implement requirements by epistemic processes. What I was looking at was a sequent calculus for dynamic epistemic logic, and I will talk about this. So first, what is an ensemble? It's somehow a multi-agent system. It's a collection of agents which run concurrently to accomplish together a certain task. Examples for this in software engineering are all kinds of e-mobility examples where several cars communicate in order to achieve whatever, to distribute in a town for finding the right parking place, things like that, or robot swarms where typical example, you have a victim in an area here on the right, you see it on the right hand side, and some helpers have to find this robot, this victim. The victim, well, cries for help, but the perception range is not the full range, so that when here you have here a victim, then the helpers down there, called workers here, will not really hear the victim. Sorry for this. Will not hear the victim, well, I'm working on a laptop, which somehow is. I'm very sorry for this. So I just will not touch the screen anymore. So they have a perception range which does not go to the workers. So, and you need landmarks for making the communication. So let me just continue how we do this. The example anyway will be very, very simple, even simpler than that. So we take epistemic logic with a knowledge modality K, an agent A knows a formula phi, and the semantics is the usual Kripke structure. You all know this, with a set of worlds and accessibility relation RA, and L gives the validation of the proposition in the different worlds of the Kripke structure. The idea is that two worlds are for an agent the same if they are in this relation R, and the K modality is satisfied if for all worlds which you can reach via R, the formula phi is satisfied. And a proof system for this is typically S4, S5, the different calculi. So they're all well-known calculi for that. So the example is, for example, the agent V, victim to be rescued by agent R, is that V knows a preposition help, but R doesn't. And so in the Kripke structure can be represented like this. You have here just two worlds. In the world W0, the proposition H holds, but not in W1. And you see here the indistinguishability relation says that R, the rescuer, doesn't know that this proposition H, whereas the victim V has only this reflexive relation in all the worlds. The victim here, this is the starting state, the proposition holds, so the victim would know this in this world. So we would have these propositions that V knows H, but R doesn't know H, and also R doesn't know that V knows H. this is dynamic epistemic logic. It's very simple stuff for all of you probably. And then what we do in dynamic epistemic logic, we add an action modality where an action says that the formula phi holds after an epistemic action u. And actions can be composed. There are also other operations. I just deal here with composition. Epistemic actions is an old approach from Baltak, Moss, and Soletsky, 1998, 1999. With epistemic actions, you announce knowledge to one or more agents. The semantics are also Kripke structures. So an action structure has a set of so-called action points or events, an action accessibility relation like the relation R we had before, and a precondition we just note with a dot here of event which says when this action can be executed. And again, the relation F says an agent A cannot distinguish Q and Q prime. And then typically we have pointed action structures in order to have a starting state for the action with this little Q here, an action structure plus a point. Well, I will use in the following just F not only as a relation, but also as the image of all action points or events which can be reached from a particular point Q here, this FA. The most well-known example is public announcement. So I have an action, call it send here. Announce the formula phi publicly to all agents, and the action structure looks like very simple. Just here we have just one action point K. The precondition is phi, and the relation is just reflexive for any element of the set of actions of A for all agents. So this is written here. The precondition is phi. So this is the representation. And the private announcement to a group of agents would be as follows. We just need another action point called N, where the precondition is true. So here you see this is again this indistinguishability relation for all agents which are not in G. So those agents not in G will not be able to distinguish whether phi holds or not, whereas phi can be announced to the agents in the group. So the formal definition is here. We have two action points. The send operation of K, if I'm in point K, gives K for those agents which are in the group, but for those are not in the group, they have this K and N, and so they will not be able to notice. So now one more little technicality, and then I'm coming to this proof calculus, the product update. So how do we combine a Kripke structure, an epistemic state, with such an action? This is also from Baltak, Moss, and Soletsky, this idea. The combination is just a product of these both structures. So the product here is, you see it here. So the update of K by U has a set of worlds which are the product of the Kripke worlds W and the action points Q under the condition that the precondition is satisfied in W. And also the relation of the epistemic relation here is also just a product relation. We relate W with W prime and Q with Q prime, then we have the relation of the product update. And of course, the validation of the propositions in the worlds is the same as in the critical structure. And composition of epistemic actions. Now, here we compose an epistemic structure with an action model, and here we compose two epistemic actions, is again this product specification. So it's just here the product for the action points, and for the accessibility relation. For the precondition is as follows. The precondition of U1 followed by U2 is the precondition of U1, and after the action U1, the precondition of U2. Also Baltak, Moss, Soletsky. So a little example for this. The private announcement, a private announcement in this little example, we have a suppose we have a private announcement of that V knows the proposition A. So we have this structure we have seen in the beginning here. V knows H, but R does not, the rescuer does not. And we update it with a private announcement of sending this little proposition that so the victim sends to the rescuer that the victim knows that it needs help. So the action of private sending is as what we have seen before. We have here two states, true here, and we send KV of H. And this yields the following structure, where we have here, this is the composition where we have here always a world combined with an action structure. Here in K, we see now that V knows H here, and R knows also H. Here with V become here, H is the same, but we see that here it's not known that it's here. It's known that R knows now that V needs help, in fact, but it is not in the same structure. We see that V does not know that R knows that V needs help. So again, these iterations of beliefs we have here. And so this is just a little introduction to the examples. Now, in order to construct a proof calculus, I'm coming from the area of algebraic specification. What we do, we construct as a little algebra of pointed epistemic actions. I just show it to you here. What is this algebra? I have an action model, and so I first bring together action models U, and in small then pointed action models. In order to have an action, I have an operation combination of Q1. I update the action point here with a new action point Q1, then I get exactly this U with Q1. Very simple here. And then I can define this point operation on the pointed action models. Here, the composition is just composing the actions models and building the product, so the pair of the both points, action points. And the precondition here is very difficult to see, is what you have seen. It's the precondition of U1 composed, conjuncted with the with after the action U1 that the precondition of U2 holds. for this F relation, the accessibility relation, a pair Q1, Q2 is in the accessibility relation of U1 semicolon U2. Well, we have a product definition if the first component is in the accessibility of U1 and the second action point is in the accessibility of U2. And we are in S4, so plus reflexivity and transitivity of this operation. And finally, we have a monoid here. The composition is associative and has a neutral element. So this was just the starting point. Now, what we did was that we wanted to prove all kinds of stuff about local knowledge. And for this, we wanted to have an idea of structured proofs. So we looked at the proof calculi which exist in this area, and there's already in 1998 Baltag, Moss, Soletsky give a Hilbert-style axiomatization. Then later they give an axiomatization by a sequent calculus, a proof sequent calculus, which needs a cut. And then the first cut-free calculus for this dynamic epistemic logic I found was in 2016 by Nomura, Ono, and Sano, who give a cut-free sequent calculus where they internalize in the calculus the accessibility relation. This looks very nice, but somehow for me, algebraically, does not make sense. I wanted to have a different calculus which works in a usual, which works in a style which in fact was based on the Hilbert-style axiomatization of Baltag, Moss, and Soletsky. In this Hilbert, Moss, and Soletsky axiomatization, they reduce dynamic epistemic logic formulas to pure epistemic logic formulas. What we tried and what we did now and to show you now is we use this for this calculus, this Gensen type calculus we have here, which uses reduction axioms in the Gensen type, but of course works modulo the algebra of pointed epistemic actions I have just shown you. So what would be the proof rules for this? You take S4 proof rules and then Gensen type proof rules, which, well, I show you all of them. Just maybe the right-hand side is always easier to read. If I have a proposition little p, in order that gamma, we have the sequence, let me say it implies, gamma implies that after u p holds delta here, then what we need to do is that if the precondition of u holds, and this implies in the sequence the p, then we can conclude that after u p is provable. With false is if the precondition holds and I cannot deduce here anything, then I get on the right hand side after u holds false. Implication is somehow the usual way of doing it. Let it do it also from the right introduction here. If after action u, phi implies psi holds, well, I conclude this that before the precondition of u must have been hold, that from after u holds phi, then in the sequence you get psi. The interesting rule is the reduction rule for the k operator. And here we do not really have the subterm property, but quite. It's very, but it's still making things simpler in the precondition. So in order to have after u ka phi holds, what you do is we push this action after the k operator, but we have to look at all points in the accessibility relation. So here, the little u here has an action point q, and then we take all q prime which are accessible from this little u, and look at these actions. So we and then if the precondition holds, this is exactly the reduction rule which Baltag, Moss, and Soletsky used in order to reduce this calculus, these dynamic formulae back to normal formulae. And then we need one rule for the composition, also on the left-hand side. If I have a composition, then it's the same as I would have the action u followed by action u1 followed by action u2. So these are the proof rules. And in order to show you again a very trivial example, we look at the example we have just seen. The victim sends to the rescuer that he knows that he needs help, also kv of h. And now when you calculate for this send action model, then we have seen that the accessibility relation is just k. It's very simple. It's just a one-point accessibility relation. Makes it, of course, very simple. So in order to show that after this SD action krh holds, we can use this R box K rule, which you have seen here, and then we get here this Q's, but since FRSD is the same, it's just the 1 point thing, we can use the algebra, and we know that from the precondition of SD, we have to prove KR of after SD H holds. Here we can again use in S4 the rule which adds the K left and right. Then we use this R box P for the proposition rule here. And that means we need to prove the precondition of this SD and H, and the precondition of H is just the formula we have sent, kv of H. So we get this, and then now by S4 we know that H implies H, which is an axiom, and we have proved that. So it's a very straightforward way of proving. And we can show that the cut rule is admissible. And in order to show that generalization holds, we prove the following admissible rule, that if gamma implies delta, then after u, gamma implies that after u, delta holds if we have, again, the precondition P, the precondition of u on the left-hand side. But there is a lemma. We can prove that if the precondition implies that after uv holds, then we can, if this is derivable, then we can omit the precondition. So with these two additional, and some induction, we can show that this calculus is sound and complete for dynamic epistemic logic. In fact, the completeness is proved by proving all the axioms of the Hilbert-style axiomatization. Now, in order to, this is this little calculus, and in fact, what we want to do here, and I have not, we want to do some software engineering with this. So we want to specify properties of ensembles in dynamic epistemic logic, and we want then to construct a program out of that. For this, we take in the dynamic epistemic logic also non-epistemic actions. We had an epistemic action here saying that the victim needs help. Non-epistemic actions would be that the rescuer really rescues the victim. And we need also a little bit more of epistemic, compound epistemic actions. We need also test, iteration, and non-deterministic choice. Also, some abbreviations for these axioms. We use the sum, the notation sum for having the non-deterministic choice of all of these actions. And if I write minus u, y, then I mean all the actions minus the one which is written here, if we have just finitely many basic actions. And so specifications are, as we did with John, specifications are as before, as usual. We have signatures and a finite set of dynamic epistemic actions now, which we will combine with other axioms, but let me stay here in this dynamic epistemic case. The example of the victim and rescuer says, again here, very simple, we have the victim and the rescuer. We have epistemic actions like, the sending action. What I need here is an action send lossy, because in this example I've shown you, it's not clear that the landmarks or the workers really get the message. Only if they are near enough, they will get the message. So we need to deal with the situation that messages can be lost. Then two simple requirements would be here to say that if after a sequence of any kind of operations, the victim cries, "I need help," then again, after some operations, the victim will really get help. On the other hand, if after some operations where not rescue have without any rescue, but it's true that the rescuer knows that the victim needs help, then it will really there will be help. So this is kind of specification of the behavior which we would expect from the system. Note that in this case, in order that in order to realize this, we need some fairness assumptions in order to get here positive answers. But just here to show you what are ensemble realizations, so programs which realize these requirements are concurrent processes, in fact, which are of the form that here, the usual thing, we have a test, after a test, certain operation is done, we have composition, operator, fixed point operator, and in particular, we can execute certain actions. Then we can say that the realization is correct with respect to a specification. I haven't given you the semantics, but it is a model of this specification. And we can, for example, construct a correct realization of this victim rescuer example, which works as follows. We have a victim process, which repeatedly, here we have this iteration, well, if it knows that it needs help, but it does not know that the rescuer knows it, that the victim needs help, then it sends the message to the rescuer that it needs help. And this conjoint with in the moment where the victim knows that the rescuer knows it, then it stops asking for help. And the rescuer, when it knows that the victim needs help, then it sends a message to the victim that it knows that the victim needs help, and then rescues the system, and then the whole thing stops. So this is a little program. I would like to have some kind of programs as proofs technique in order to get this program out of such specifications, but this is future work, and maybe we can do this together with John. So I talked to you to John's John's inspirations, which I got in the work with him, namely extending the lambda calculus with first order constraints and extracting structured programs from specifications. It's a very nice way of working together. And then I started some little research program on epistemic ensembles, where I presented you a cut-free sequent calculus and started to show you how one can construct correct programs from dynamic epistemic requirements. But the most important thing is that I thank you, John, for all the time we could work together, discuss together, for all your help. And from very far away, I send you all my best wishes for many very successful and happy years in the future. Thank you very much.